Hello.
Hello, good young sir. How are we doing, Conrad? How's it going? Can you hear me okay?
Hello, sir.
Hello. Can you hear me fine now, Conrad? Aloha. Hello. Yay. I can see you. Can you hear me?
Good. Very good. How are you?
Yeah, I can hear you okay.
Connection. It's a bit dicey.
Right, okay. Sometime.
Hello.
Hello,
Yeah,
can
I
you hear
can
me?
hear you.
Okay,
I
awesome.
think the screen's a bit frozen.
Yeah, your screen appears to be frozen, Conrad. Your picture's gone into freeze mode. Okay, good.
Yeah.
We're back onto winning ways. So give me a bit of an update. Obviously got the good news about it being quite a decent paper. Any results yet?
Yeah. I think I got given like half of the test, which was
Right.
like an okay mark. It's just with some of my prefixes.
Yeah.
I would normally get the correct numbers just to the wrong powers.
Got you. So
Silly mistakes like that. But
yeah, okay.
I definitely passed. My teacher said I definitely passed.
Good.
I haven't gotten my second pass back yet.
Okay.
But we'll see.
Okay.
Yeah.
Presumably they're still deciding grade boundaries before they finally decide what grade they give you for the overall grade, right?
Yeah.
Right.
Yeah.
Okay. Well, keep me posted on that. But also, I
Sure.
very much appreciate the fact that you're telling me some of the areas where marks were dropped and such, because it's very important
Yeah.
to reflect after the whole exercise, really, and then try and build on it. And of course, the nature is that everything is quite what's the word? I don't want to say hostile. The pressures are quite immense, so to speak, because it's a very short
Yeah.
time, and then you quickly have to reflect and then act. Give yourself some actions, and then see if that puts you on a better track next time. But this is
Exactly.
definitely something we are also going to try and look at. Make sure that when we have
Yeah.
questions, you get enough questions to practice prefixes. Is that okay?
Yeah.
Awesome.
Yeah.
So you said you wanted to either, well, we can try and
Well, just to
screen both waves and quantum, or if you want, we can go for
yeah.
quantum first and then finish off waves. It's really up to you what your starting point
I
is.
think let's do waves
That's
first.
absolutely fine.
Oh, and also, you met Eddie.
Yay! Yeah,
Eddie,
I
yeah.
heard from Eddie. Thank you. I was about to update you on that. Yeah, cool. So he says, yeah, though you say it's gonna be easier.
Oh, 100%. Yeah, he is way smarter than me at physics. I'm trying to catch up to him. Yeah.
Well, I tell you what, it's good to have smart friends like that because there's always
Yeah,
something
it
to
is.
learn from them as well. So good stuff.
Yeah.
So as a bit of a warm up, then, because we're gonna go through waves. Do you want to have a go at this question? And also, if you have any questions, by the way, Conrad, if you have some past paper questions, remember you can share them with me via the chat. I can upload them onto the board and we can have a discussion. So remember that we can have a two-way interaction in that form as well. So here is the question. So it's clearly not your kind of conventional type of problem because you've got options all the way to H. In other words, they have drastically reduced the monkey factor. The odds of guessing are reduced high, or rather of guessing and getting it correct are reduced tremendously. Well, I was just get a glass of water.
Yeah. That's interesting. Wave press Q 2.5. So it's gone 1.5. The time is so 3.5 over the frequency. I mean, my guess, which is the only answer I've actually got, which is probably not right, is E, which was
4.4.
Yeah, I don't know. They're like a weird way, which I'm not too certain about.
Yeah, don't worry. And really what I've done here, Conrad, in just to kind of I've thrown you a bit in the deep end, okay? But it's okay to be thrown in the deep end with a subject like physics, because I have this actually, to tell you the source of this question. These are the Cambridge University applicant test questions.
Wait,
so they are year 11 and year 12 standard. They're not year 13, and they're on non-calculator. So they deliberately choose the values so that you can do this quickly without a calculator. But
so wait, what would be the answer?
The answer is F.
F. I see. Interesting.
Okay, so should we look at it together just to explore how to think about it? So it dips into water every 0.8 seconds. So what is this 0.8 seconds representing?
Would that be the frequency?
And that is what we established. So it's not, this here is the time period.
Oh, okay. So I have to do the reciprocal then to get the frequency.
Correct. And how do I know that it's the time period? Because also the unit gives me a hint.
Yeah.
Because frequency is measured in hertz.
Yeah.
Or units of per second. Why are the units per second? Because frequency is the same as 1 divided by time is frequency. Now the units of time are second. So the unit of frequency, strictly speaking, is s to the power of -1, but we call this here hertz. So we know it's definitely a time period. There is no question about that. So the reciprocal of that, yeah, you're right, 1 divided by 0.8, which is 5/4 hertz. So that is the frequency.
Yeah.
Now there's a number of ways we can do this. We can either try and do it a bit intuitively, or we can use equations to churn out the answer. What do you want to look at? The intuitive way or the calculation way of approaching this problem? We can look at both if you
Maybe.
wish. Why not?
Yeah, let's try both.
Let's look at both, because then you can check
Yeah.
which one makes more sense to you, so to speak. Yeah, you're going to have that option.
Yeah.
So this dipper or this stick is dipping at position X. Just trying to understand the problem. So it's dipped in, and then this wave crest has traveled 2 centimeters at this time when we took that snapshot. We wait 1 second later, and this wave crest Q is now here. But another wave crest, because it's dipping in, has also been produced. And it has traveled 3.5 centimeters. So let's just look at it from the calculation point of view first and think about what tools we're going to need. And as per usual, we're going to, if we were doing this and they had to show our working, then this is what we would follow: formula, the working, the answer, and of course the units. But it's a multiple choice question, so we'll keep this in our mind and we'll be thinking of formulas. So what formulas are going to be relevant to this problem, solving this problem? What formulas do you think would be helpful to have?
B equals F lambda.
Absolutely
maybe.
spot on. Absolutely spot on. V equals F lambda. This definitely will be needed because they're asking for a wavelength. Any other question? Oh, sorry, any other equation that may come in handy? This is not so obvious now. The next part is not so obvious.
Let's try not so obvious. Maybe velocity equals distance over time or something.
Spot on, Conrad. Spot on. Spot on. S over T, or in other words, we can say that S is equal to VT. Very good. This here is not so obvious, but it might just save the day. Why? Because we know that this velocity, that this wave has a certain velocity, and we know what distance it's traveling, and we know what time it travels that distance in. So in other words, if I rewrite my equation and say that 2 centimeters using S equals VT will be equal to the speed of the wave multiplied by the time that elapses.
Yeah.
Here's the speed of the wave, and this here is the time T, which I've multiplied, must be equal to 2 centimeters. Note though that my velocity is definitely in centimeters per second, because this distance here is in centimeters. So please be aware of that. So far, so good.
Yeah.
Excellent. The next thing now, so we see that we have 2 unknowns. We don't know what this time T is, neither do we know what this velocity is. They're 2 unknowns. So if we have 2 unknowns, then it would make sense to try and form a second equation, because if you have 2 unknowns, you need 2 equations to find out what they are. If you have 3 unknowns, you need 3 equations, 4 unknowns, 4 equations, so on and so forth. So this here we can label as our first equation, equation 1. Can we now form another equation using this diagram? So we formed equation 1 using that diagram. Can we now form another equation, equation 2, using this diagram? And what might you propose that equation might look like?
I would
using the same idea of S equals to VT.
Yeah, so I would believe S would be 3.5 perhaps, or would you add the 2?
Would you add the 2? All right, now let's just ask ourselves. Yeah, I know this is this one here is really the deal maker. So what is this distance called from this crest to a next crest? From one crest to another crest, what is that?
Would that be the wavelength?
Very good. So look, this wave crest Q, what distance has it traveled in a time T plus 1? What distance has it traveled in a time of T plus 1?
Distance.
So it was originally formed right at X at time. Yeah. And then at time T, it was 2 centimeters away. And then at t plus 1 now, it's moved over there. So what is that total distance? I'm going to help you out. Note that this here is 3.5 centimeters. So what
I just
distance?
add 2? Or
you wouldn't add 2. So the distance from x of this wave front. What is that distance from x?
Would it be another 3? Right?
So here the distance.
I don't know.
Don't worry. I'm going to break it down. Let me ask the question differently. Okay. So here, this wave crest had traveled 2 centimeters. In a time t. But look where it is now at a time t plus 1. How far is it from x is the question I'm asking. How far is it from x? Just using this diagram. Use this diagram. How far is it from x? How far is that wave crest from that point?
In centimeters.
Just using what's represented here. How far is?
So, from the first diagram, which confused me a bit, no, I'm so lost. Sorry.
You're lost. Don't worry. So it is from x. It is 3.5 plus lambda. Is this lambda we want to find? But we don't know what the lambda is. But we're still going to write it. So we know how far this wave has traveled from x. Just like we know how far the wave has traveled from x. That traveled 2 centimeters. After t plus 1, it travels 3.5 plus lambda. That's the distance from x. This must be equal to v, the speed, multiplied by the time that has elapsed. Does that equation make sense?
Yes.
I hope it does. Excellent. So this is equation 2. Following so far? Next, now we say 3.5 plus lambda. We expand this bracket. Is equal to vt plus v. But hang on. I know what vt is. Vt is 2. So I'm going to replace that with 2. Now, what is v? Well, we know that v here, we can express it in terms of lambda. V is the same as f lambda. So we can write this as f lambda. Why am I doing that? Well, it means that I'm only going to have one unknown in my equation, only the lambda, because I know what f is. F is 5/4 hertz. I calculated it here. Now we write the expression using what we know. 3.5 plus lambda is equal to 2 plus 5/4 multiplied by lambda. This is the frequency. That's lambda. Good. Group the like terms together. Take that 2 to the other side. 3.5 minus 2 is equal to 5/4 lambda minus lambda. 3.5 minus 2 is 1.5. This is 1¼ minus 1, which is 1/4. So this would be, okay, 1/4 of lambda. And we can represent this as 3/2. So to solve this now, if lambda over 4 equals 3/2, then what must lambda be? We cross multiply by 4 on both sides. So lambda equals 6 centimeters.
That makes sense from seeing you do it. Definitely makes sense.
Okay, now let's approach it from the intuitive way.
Because I was very puzzled when you were asking me, because I thought you wanted the exact centimeter distance.
I see. I should have made it clear to say only in terms of what's written here.
Right. Okay.
I should have made. If I added that, you'd have had a little bit more of a hint of how to go about it. You're right. You're absolutely spot on there. Intuitive way of looking at it now. It's dipping every 0.8 seconds. So you got to really now imagine this, because now we're throwing away these numbers now and all these calculations. So we really have to get in touch with the problem. So every 0.8 seconds. So let's just think about it. If we took this picture at a time t, and then we waited 0.8 seconds later, but we're not waiting 1 second, please note. We're going to wait 0.8 seconds later. Why am I waiting 0.8 seconds later? I'm doing it deliberately because I know that is a time period. So when another wave is produced 0.8 seconds later, if we draw it here like so, the distance between these two must be exactly a wavelength.
Yeah.
Because remember that your wavelength, lambda, is really just another way of looking at the time period. Because the distance from there to there, if the axis was labeled in meters, would be called the wavelength. If the x-axis was labeled in seconds, this would be called the time period. So t and lambda are just one way of looking at the same quantity, but in different dimensions or coordinate systems, shall I say. Lambda uses a coordinate system where you're using meters on both ends or on the x-axis, whereas time period uses the coordinate system where the x-axis is in seconds or minutes, but it has to be a quantity of time. Good. So we know that after a time period, this here would be lambda, because t and lambda are related in that way.
Yeah.
Are we okay with that?
Yeah, yeah.
Excellent. However, we see that, hang on, where is this? Sorry. Where are we at here? Yeah. We see that this here has traveled a further, sorry, there's now a further 0.2 seconds added to 0.8 to make that 1. Now,
So
what fraction of 0.2 is 0.8?
What fraction is
of 0.2 is 0.8? And there's a reason why I'm asking, because physics, remember I said the key mathematical issues are ratios. So what fraction of 0.2 is it? Or 0.2 to 0.8 is a quarter, isn't it?
Yeah.
So we know that during that extra 0.2, it's going to travel quarter extra of a wavelength.
Yeah.
Because if it's quarter of a time period, it must be quarter of a wavelength. So this here is half a wavelength, and this here is quarter of a wavelength. Are you okay with that? Because it's quarter of a time period. 0.2 is quarter of a time period. So whatever distance it would have traveled extra will be quarter of. Does that make sense?
Yeah. So
what is the extra distance it traveled? Well, the extra distance it traveled was 3.5 minus 2.
Yeah, I was just confused because if you're saying it's if it's a quarter of the time, it would be a quarter of the.
Yes. So in other words, what I'm okay. We'll rerun this script here.
I guess. Could you? Well, I know it wouldn't be right if you just did 3.5 times 4, because that's obviously not correct.
You're absolutely right. That's obviously not correct. And this is now where we're going to bring in that next piece of the jigsaw now. And we're going to say, okay, so what I'm trying to say here now, in other words, Conrad, I'll use a different phrasing for it. I'm saying if this picture had been taken 0.8 seconds later, then the distance between the two crests would be a wavelength.
Yeah.
Does that make sense? However, because this has gone over 0.8 seconds by 0.2, this wavelength or this wave would have traveled a further, if you like, quarter of a wavelength, because 0.2 is quarter of a time period.
Yeah.
Are you okay with that? That's the part I want you to get.
Yeah.
Because this 1 second is over 0.8 seconds by 0.25, sorry, by 0.2,
okay.
by a quarter.
Yeah.
So it means then that, like I'm saying here, the extra distance that this wave would have traveled, and what's the extra distance that wave crest Q has traveled? It's 3.5 minus 2, which is 1.5. So 1.5 must represent quarter of a wavelength.
Yeah.
Because that's the extra distance it's traveled. And we know that that must represent a quarter of a wavelength. So the wavelength must be 4 times 1.5, which is 6. This is,
okay.
Yeah, so that is the intuitive way of approaching it. So which way makes more sense to you or feels more natural?
The one that makes more sense to me would probably be the equation one, which kind of, when looking at it, it kind of, okay.
Yeah, because the maths does everything out for you. Whereas with the intuitive one, you really then need to know all these extra nuances. So this without a doubt is a little bit more challenging to process, I think. But I wanted to find out from you. Excellent. So a few tricks here to remember. That's just the reason why I introduced it. Now, where we left off from last time, if you can remind me, we had looked at interference and we had looked at Young's double slits. How did you get on with exercises and questions from there?
I did some ones with the practice paper.
Did you find any of them tricky?
Yeah, some were quite challenging, but I just kept on trying them over and over again. And I did this Isaac physics. Have you used Isaac physics ever?
Yes, absolutely. I use Isaac physics. It's a big thing we use at our school because we always I'm the Oxford and Cambridge coordinator at my school, so we always send off 15 kids to Oxford and Cambridge, so they have to use Isaac physics because then they can become like residents and go for workshops. And if you do a certain number of exercises and if you get a certain mark, then you get invited to go and attend some workshops and such. So it's a big part of what we use at school.
Oh, well, that's very good. Yeah, I just did a few questions on there.
Good.
So it was all right. It was all right. I sort of got the hang of it after a bit.
Excellent. So are you saying then that you're okay with that side of things? Because the only thing then outstanding on this one then would be, what about stationary waves? How are you with that?
Not as confident. I just think in general, I just guess it's sort of just like tricky wave questions. You know, really depthy ones are the ones I struggle with.
Okay.
Just in general.
Okay. So of the papers I sent you, did you have a look at those wave questions, and was there anything in there that you found particularly tricky? I sent you about 3 papers.
Let me
wave
just
questions.
Check my thing. I think I actually did.
While you're doing that, I can dig up some more.
Just bring up the specific one. Which one was it? It was from the 2018 breadth in physics.
Yeah, okay, let me just go to that one.
It's
2018. Let's look for Conrad in here and I'll get those to you. Breadth in physics, there we go, super duper.
Basically
2018.
25. 25 and like,
oh cool,
25 and like 26 and all.
25.
Those ones were very were quite tricky.
A little bit tricky. Let's go for the tricky ones. We love tricky. 25. Okay, cool. I'm just going to bring them through. Let's bring this, and just give me a moment, right? And then I'll just bring this through, and then that should give us, once we've gone through this, we should have some time to then finish off our stationary waves and such. It's not so bad, stationary waves. It's just more the formulas that are there to remember, and then you just need to remember the properties of them, really, Conrad. So don't worry about it. We'll get there in today's session. 25, super. Here we go.
I remember getting the stationary wave question right on the breadth paper.
Yeah, good.
I think that would probably
it's more factor. There are some calculations.
Yeah.
You know, when you've got open pipe.
Which would be, I guess I need a bit more.
Bit of a boost.
Yeah.
We're gonna give you just that. Where are we here? Oh, come on, where is this hiding? Ah, there we go. Just bear with me. I'm just bringing the questions through. Yeah. Shows 2 loudspeakers. Blah 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 blah. The points being at different distances. Right. 26, 25. So that's there. And then part. Which part is that now? Is that part C? Right. Okay. Point P. Da 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 da. Phase difference given. All righty. And can I squeeze that in there? So let's look at the first part then. If you want to work out what the frequency of the wave is, what might you do there?
Look at the time period of the wave.
Yep.
And then do the reciprocal of that time period.
Spot on.
So I look at.
Is it 25 and 26 or just 25, by the way, Conrad?
Sort of, I would say both, but a bit challenging for me.
Yeah.
I wasn't too confident on either.
Think around these problems. So the first part here, firstly, what are the components of an oscilloscope? So we have the gain control and the time base. Yeah, this here affects, if you like, the scaling intervals on the y-axis. Essentially just a glorified graph. Time base affects so it says describe how the trace on the oscilloscope can be used. Scaling here affects x-axis intervals. So you know that, excellent. And you've said the right thing. It's 2 marks. So firstly, you would use trace to determine time period. Okay. And 2 marks here. And then you can say for the next one, frequency can be calculated, calculated using 1 over time period, and this time period must be in seconds. So remember, normally when you set your time base, you can set it either in milliseconds, microseconds, in seconds. So you have to know what your base setting is so that then you can use the right quantity in there.
Sorry, 1 sec.
That's okay.
Sorry, my dad keeps forgetting I have a
class
tutoring lesson.
That's all right, don't worry. Okay, next one then. What's the next one? So you're okay with the first part, and you got it pretty much.
Yeah, that makes sense.
There. And normally the first one is there to ease you into the problem and kind of like usher you into the challenge, as it were.
Yeah.
Right? Okay. So figure 25.1, just two loudspeakers. L1 and L2 connect to the same SIG gen. Okay. So if they're connected to the same SIG generator, what's this telling us?
They're coherent, perhaps.
Correct.
Or they have the same frequency. Yeah.
Yeah, the coherent sources. Awesome. So here already, we haven't even finished reading the full question. We're thinking interference.
Yeah.
Yeah, two sources. The loudspeakers emit sound of the same wavelength, but with different amplitudes. Ooh, right.
Same wavelength, but different amplitudes. Yeah.
Okay, very interesting. Very, very interesting little problem.
Very interesting. Yeah.
The points P and Q are different distances from the loudspeaker. All right, let's really get our head around this thing, Conrad. The sound at P from L1 alone has displacement X1. I'm just going to try and underline things here. So L1, L2, same wavelength, different amplitudes.
Yeah.
Okay, we've got that. That's okay. The sound at point P from L1 alone, okay, has displacement X1. The sound from L2 alone has displacement X2.
Yeah.
Figure 20 shows the variation of X1 with time, right? But we don't know which one is the lower amplitude. Well, okay, let's keep going because there's no question here anyway. They're just telling us.
Yeah.
Right, okay. At this point in time, we should also look at the graph. Axis micrometers, 10 to the minus 4. Okay. Just always when you have a graph, look at the axis first, just to make sure that you can then have a better idea of what's going on. The sound from L2 alone, okay, at point P has amplitude of 1 micrometer and a phase difference of 180 degrees compared with the sound from L1 on the same frequency as L1. Draw the variation. Okay, actually, it's not as bad as they try to make it out with all these extra sentences about telling us things. So we know what the amplitude is and we know what the phase difference is. Okay, cool.
Yeah.
Same frequency. Cool. Okay, off we go. So amplitude, that's my amplitude.
0.1 is only 1 micrometer.
Correct. And -1. Frequency will be the same, isn't it?
Yes, with the crest of the wave start at 0 on the x-axis.
You're right, because they are in
180.
antiphase. They
Yeah.
are in antiphase, meaning
crest would be.
when this is up, the other wave must be down.
Yeah.
Yeah?
Yeah.
So again, the reason why I'm drawing these dashed lines is just to make my sketch much quicker.
Yeah.
All right. And here we go. So we've got
yeah.
Was. Okay.
Yeah.
That's how we are going to do that.
Yeah.
Cool. And is that what you did for that one?
Yeah, that's basically it's kind of as far as I got. Yeah.
Yeah, good. And the reason why we've done that is because it says they are in antiphase.
Yeah.
Good. Explain why. Oh, draw the very. Yeah, we've done that. Explain why the intensity at P due to the sound from L1 and L2 is not the same as the intensity of the sound at P from on. Explain why the intensity at P due to the sound from both L1 and L2 is not the same as the intensity of the sound at P from L1 alone. Right. Okay. 2 marks. How are we going to explain this one?
My first thought would probably be constructive and destructive, or just any
good. And you absolutely spot on, because we don't, well, if they're out of phase by 180 degrees,
yeah, they're gonna
absolutely. But that's not even why I just say is explain why the intensity is not the same. They're not saying why it is less or greater. So we just need to explain why it is not the same, why it is different.
Yeah.
Sometimes when you're answering these questions, sometimes it's good to state the obvious, because these are explained questions, and these are the questions A-level students struggle with. So I would almost start off with saying intensity is proportional to the square of the amplitude.
Yeah.
Yeah. It's almost the first thing. Now, I might get a mark, I might not get a mark, but I will state the obvious first. So intensity is proportional to the square of the amplitude. Now I'm going to talk about what happens in terms of the amplitude.
Yeah.
So when sound source, both sound sources, both sound sources, you can say, will superimpose at, what is it? P? Yes.
Yeah.
Yes, they will superimpose. Or you can also use the word they'll interfere. I always used to have this debate to say, what's the difference between superimposition and interference? And it just used to go crazy in the department. So I don't think I've come quite to a conclusion.
I think superimpose sounds smarter. So
yeah, I know.
I'll probably go for that one.
I used to say that. I think superimposition is a principle, and it's like a mathematical principle, whereas interference is a phenomenon.
Yeah. I just think
I used to get all sorts of arguments. So that argument was never closed, unfortunately. So we had to disagree to agree. But that's still my
I think the best word that a normal person wouldn't understand would probably be the best bet.
Yes.
I think.
Yes. No, I'm
probably be the So superimpose is
superimpose, that's fine.
We want to go.
Absolutely. Both sound sources will superimpose at P to give a resultant wave. To give a resultant wave. Formed of the sum of the displacements. Running out of space. From the sum of the particle displacements at each point with a different wave, with a different amplitude.
Yeah.
Okay, forming a resultant wave. To give a resultant wave formed of the sum of the particle displacements at each point with a different amplitude. Right. 2 marks in there, I think, must be in there somewhere. I can possibly see this.
Yeah, I would.
I'm coming at this code. I'm not you looking at the mark scheme or anything like that, Conrad. I'm literally so that you can see the thought.
The
thought process as opposed to just go into the mark scheme.
So
the wavelength of the sound is 34 centimeters. The distance L1 to Q is 200, and the distance L to Q is 217. Explain the type of interference occurring at point Q.
So if
the wavelength of the sound, so they've given us lambda. Just going to write a few things here. Lambda equals to 34 centimeters. If we just go about explain the type of interference occurring at point Q, let's put some values here. L1 to Q is 200. Was it 217?
217. Yeah. And then difference of.
And what's the other 17. One, please? If you just let me know what that one is, Conrad. I'll have to go. Don't worry. The other one is, what's the other one? No, L1Q is 200, the other is 217.
Yeah.
Sorry.
Yeah.
200, and this is 217. And we've been given that lambda is 34 centimeters. By the way, I've drawn the arrow on the wrong place. Big mistake. Definitely want to draw the correct diagram for starters. Okay, there we go. Looks more like it now. 200 centimeters. And that's the wavelength there. So what's the path difference?
The path difference.
In terms of,
since it's 180 degrees out of phase, could I say 17?
Yeah, you're right. So we're going to say delta X is 17 centimeters. And in terms of a wavelength, 17 centimeters is half of 34. So we can also say that it is also half a wavelength.
Yeah.
Now, this also corresponds to a phase difference. Half a wavelength phase difference corresponds to what?
180. Oh, half 180.
Correct.
Yeah.
Or a phase difference of 180 degrees.
Yeah.
Now we need to think about what's taking place. So if they're now out by 180 degrees, what's now going to happen if they're out by 180 degrees? So already they're being produced where they are out of sync. Now by 180 degrees, that's what it says. It says the sound of that. So sorry, I see. The sound at P. So this is it. And then that's the sound at, oh, it's not so bad, this question, actually. Maybe we're overcomplicating it. Maybe we're overcomplicating it for 2 marks. So surely they've already told us, they've even shown us what the phase difference at P is. It's like we've gone the round way and done it and then found it. We don't need to do that, seriously. So they've already given us. So if they're out in phase by 180 degrees, thank you. What are we going to say here, Conrad? Complicated.
They will destructively interfere. The amplitude will sort of you would add the amplitude since
oh God, I've just made a blunder. Oh dear,
what's
I'm going to and fro. It's to Q. Oh dear.
No, to Q.
It's to Q. Sorry, literally, it's to that. I was going because I'm going between 2 and 3. If I had it all on one page, it's different. It's you. Sorry.
Yeah, it's
there.
No, I should have also.
Yeah. It's been a long week for all of us. So it doesn't change the maths anyway. You're absolutely spot on.
Yeah, it doesn't.
Right, excellent. So we know here that delta X, the path difference, is lambda over 2. And this here will correspond to a phase difference of 180 degrees.
Yeah. Yeah.
Now,
so
we don't know what the distance to P is, but we know that when they are at P, what we get is destructive interference of some sort. It's not perfect destructive interference because this has
they've got different amplitudes.
Correct. Yeah.
Yeah.
So it's not going to be complete. Whereas here now, the waves are now going to move, are going to be 180 degrees out of phase. So in other words, this wave here is going to move and be 180 degrees away from this wave. But if we move it 180 degrees, so this here is 180 degrees. So if you shift this up to 180 degrees, move it forward, because it's going to be 180 degrees now. It's a nasty little question, this.
It's not, it's a tricky one,
No, it's a nasty question. So now you can see, hopefully, that when you shift one of them by 180 degrees, they're now aligned.
Yeah.
So actually, we get constructive interference. It's a nasty question.
So, yeah.
It has to be constructive interference. Right, at this point now, breadth in physics. Which one is that one? 2020, no. 2019. 2018, did you say? Got to be, has to be.
Show it.
Okay, we got that part there. Path difference is 17 centimeters or half wavelength. No, I disagree with the mark scheme.
Yeah. So normally, yeah, sometimes the mark schemes are a bit.
Hang on, I disagree with the mark scheme there. So, hang on. 217, 200. Now, what we're saying is if at P, there is destructive interference and they're out of phase by 180 degrees.
Yeah.
Because no, OCR, I'm not in agreement with that. If I have two sources of waves, and let's imagine that they are out of phase by 180. Well, let's say that they are in phase. These are my two sources. Do you agree that here, a point that is equidistant between the two waves, this will be constructive interference? For a point that is,
yeah,
because the path difference is 0.
Yeah.
However, if these are 180 degrees apart,
yeah,
it means that when this guy arrives here, he's going to be at a crest, and this guy here will be at a trough.
yeah.
So if these sources were 180 degrees, you would not get constructive interference there.
No, you wouldn't.
You get destructive interference.
Exactly. They
and
would.
Exactly the same situation that's happened here. Because these two waves, hang on.
There's a
Conrad, my brain
It's been
is
a long
starting
week.
today.
It's been a long week. Don't worry. Don't worry. It's
Okay.
been a very long week.
Okay. So have you understood what I've just told you here about this? Because this is
yeah, I've understood that. Yeah.
Excellent. And the only time you see these kind of questions where they give you these things in different phases are normally with the Oxford and Cambridge interview questions. They like asking where they give you different phases. So that's where you need to use that skill. But they've been so cunning in this question because what they've told us, and I'm now really dissecting the whole question properly now. What they've told us is that they've simply told us that, well, if they're connected to the same generator, that's the key thing. They are trying to say, please note that the phase difference is 0.
Yeah. Path.
That's what they're saying.
So what does the mark scheme say for the type of interference at Q?
So the
you say
scheme says there's going to be destructive interference.
Destructive, yeah.
That's what the mark scheme says.
And
why I'm now going back to my drawing board with you is to say,
yeah,
the reason why is because, and they're being very crafty, these are coherent sources. So they're connected to the same signal generator. So they are in phase. So the phase.
Yeah, so they don't. Yeah.
But they gave us a random place. And in this random place, there is destructive interference taking place, not total, just partial. Then they've given us another place here. Now, what I thought they were saying here, the sound at point P has a displacement X, where I got thrown out in reading the question in rather in a bit of haste, was where they said there is a phase difference of 180 degrees. I took it that this is a phase difference at the source.
Oh, okay.
So I thought that saying this and this are out of phase by 180 degrees.
Oh.
In which case, where you would get constructive interference. But actually, reading the question again, these two are in phase. They just happen to have a path difference that leads to destructive interference at P.
Yeah.
So now here, when I look at this scenario, and I know that 17 centimeters is lambda over 2, which is 180 degrees. A phase difference of 180 degrees means destructive interference. If two sources have a phase difference of 0,
yeah,
if the two sources have a phase difference of 0, it means if they have a path difference anyway of lambda over 2, they will, or anything of n plus 1, n plus lambda over 2, you know that formula for.
yeah.
Yes, then
they'll just cause destruct, because they're always going.
Oh yeah, I made an error there, but it simply goes to show that it's
don't worry, we will have these days.
Yeah,
I can only imagine an exam week as well, where it's just lots of.
Got to do this in all the tension and everything.
Yeah, yeah.
So that's done. That's destructive. So we say here destructive, and we know why. Okay. So they threw me. This phase difference of 180 is not at the source, not source.
So I have a phase difference of 180 at P.
This is only at P.
Why? How's that at P? I'm trying to think of how. I guess since it's changing the angle of the.
Yes, you're at a different angle and you're moving along.
So that would kind of change the. Yeah, okay, that makes sense.
So they threw me off when I read that there's a phase difference of 180. I thought this was at the source, but this is not at the source. So therefore, this would be destructive.
Makes sense. It does make sense.
Oh, good question.
That's a tough one. It's a tough one.
I know. Tell me about it, but what a question. Good, good question. Right, moving on into 26. That is a tricky one, Conrad. That is a tricky one.
It's a tough one.
But you see, even then, you can still give yourself some credit. You would not have lost all marks.
Yeah.
You would have probably dropped, this 2 marks. Or even me, if I was doing it and I was doing it in a hurry, I'd have dropped these 2 marks. Yeah.
Yeah, I mean, it was
but would have still
think about it a lot.
And of course, we'll win some, we'll lose some. As long as it's not diabolical where we're throwing away 6 marks in one go. 1 mark, 2 marks thrown here or there is not the end of the world.
Yeah.
Right. Shows an arrangement. I made a sheet in a white. Okay, what are we going to do for this one? Just looking at this one. What do you reckon you'd do for this one, Conrad?
Read it again. What would I do for that?
So with this one, again, just think formula. What formula do you reckon you would need to use? Just look at what quantities have you been given as a bit of a starting position.
I've given frequency, and the unknown is the wavelength.
So can we think of a formula where there's frequency and there's wavelength as well?
Yeah, V equals F lambda. Or
correct, spot on. Yeah. So are we now going to work out lambda, because we know that lambda is V over F?
Would the microwave transmitter, is it in a vacuum?
It's in air. They haven't told us yet, which is really, really like not nice of them. We will assume.
Can we say it's
in air?
It's on the electromagnetic.
Spot on.
We can say it travels at the speed of light.
That's exactly what they want you to do. That's why they're not giving it to you. They want to see if you know that it travels at the speed of light. Correct. And prefixes, go on then. A chance to out. Is it to
the 9, or was it to?
Spot on.
Is it? It's a 9. Okay, good. Good.
Yeah, absolutely spot on. So 11 times 10
Yeah.
to the 9. Okay,
Fine.
and in hertz. Good. And so you divide these two and you get the answer for lambda there. So far, so good?
Yeah.
Okay, next one here now. How would you explain this one?
When it goes through the slit,
Yeah,
it's like diffraction. Is it? It
absolutely. It's
is
going through a slit,
diffraction, yeah.
right?
So the waves, I wouldn't really know how to explain it,
So
really.
let's look
I
at this.
have it
What
in
did it
my
say?
head.
Shows an arrangement used to do. Okay, metal sheet with a wide slit. There we go. Microwave
Yeah.
transmitter, wide slit. Right, okay, we're okay. Okay, I don't know what this value is. It might help to calculate this value. What is 3 times 10 to the 8 divided by 11 times 10 to the 9?
Just quickly get that equals 0.03. I'll just round
Okay,
up.
0.03 meters, which is how many centimeters? Which is 3 centimeters.
Yeah.
Okay, cool. Let's go over here. It says with a narrow slit width of a few centimeters. Ha! The position of the transmitter, receiver, and the metal sheet are unchanged. So there's your receiver. Ah, there we go. I didn't even see that. So that's where the real receiver is, because I'm going with the receiver. Okay. We've spotted the receiver. Good. We know where it is. Explain why the receiver
I
now
wish that
decides
was one of the
microwave.
questions.
Yeah, I know, man.
Circle the receiver. That
Circle
would have
the
been one I
receiver.
could.
So explain why, because I was going, where's the receiver? Where's the receiver? All right, good start. Explain why the receiver now. You mentioned the key word, okay? Because now slit width is comparable to wavelength of microwaves. We can then say that diffraction is more pronounced. And so the microwaves spread out more and can now reach the receiver. And now reach the receiver. Unlike in the first case. Unlike in the first instance. Okay?
Yeah.
Super duper. But you knew the idea instantly the moment you looked at it. All right. Now here again, there's no harm. You can explain, you can use or talk about the value that you just calculated. Yeah. So you can say that lambda of this is whatever, 3 centimeters. This is a few centimeters. So you can throw in the value that you'd calculated. But what they're going to be looking for is diffraction, the fact that the slit width is now similar to the order of magnitude of the wavelength. Those are, you're going to get 2 marks here.
Brilliant.
Okay.
Yeah, it makes sense. Yeah.
Yeah. But I'm hoping that you're finding the exercise useful, of you seeing me solve questions cold as well, to show you that
definitely right.
You know,
I think the most helpful bit is just sort of seeing the process of just going through
absolutely
and
the process.
sort of just adopting.
I made a mistake there. I've got to go back. What did I not read? What's just seeing somebody go through those nuances and what else you need to consider. But it's really we've gone through that. So unfortunately, we didn't get to start stationary waves, but there is no rush. I think it's better that we really make sure that we are thoroughly grounded, and in terms of any issues that you're finding or struggling with, we address that, and then we can move on to stationary waves. You're in a midterm break as well now anyway, isn't it? So will you a little bit more flexibility.
Will you still be able to do another session on Friday?
Yeah, absolutely. Absolutely. So the best days, are you planning on going out or venturing somewhere nice, or?
I think I don't know. I'll ask my parents. But right now I think any day is suits.
Fantastic. The only days I would probably try and okay, so let me see. Any day, Monday, Tuesday. Actually, no, Tuesday would be out because I am taking the little one on a little adventure. So that would mean any day, Wednesday, Thursday.
Yeah.
Wednesday or Thursday.
I'm just asking
any of those days.
my parents if what days.
Well, look, we're gonna liaise. You got my number. We're definitely gonna make
exactly.
a plan.
Yeah, we can discuss
so like I say, I'm super flexible because it's holidays. So even if you said, look, can we have the session in the morning? I'll be like, yeah, that's cool. And the good thing about in the morning is that I won't be as tired as I am. So my brain will be firing. Will be firing a lot more rapidly and a lot more accurately. That I can assure you. It's just, I've been sorting out trips, and then the year 13s, they had their exam yesterday. And it's a funny thing, unless you are a teacher, when your students go and sit an exam, you do feel a certain level of anxiety as well, because you don't know what the paper is like, and you are hoping that they don't come out with very sad or long faces and just feel like, oh, that was horrible. So yeah, I was in a bit of a tense mode, and parents were coming to me, and you know, like the like before the exam, leading up to it, every single day, because they stood down, so they weren't having lessons. So they would just be asking me questions from different examining boards, bringing past papers, and it was just like my head was going all over the place. Oh, literally, like I rarely get my head being
100%.
around.
I think also a good way I can sort of improve the grade is, now that you're teaching Eddie, you can sabotage his grades, so it brings the grade boundaries down. So we can talk about grades later. It was a big plan all along.
I like that one. Right, that was definitely one of the best ones today. Like the way you're thinking, Conrad. Super stuff. So I'll be picking up Edwin pieces with Eddie. Unfortunately, it might not be this part of the half term. You might have to wait a little bit for that until after he's finished. Are you doing the same subjects as Eddie?
It was
Are you guys doing the same subjects, like physics and the other subjects as well?
No, he's actually doing all the sciences and maths, which is probably much well suited to sort of physics. Wow. I'm doing physics, just chemistry, such a weird, biology, odd range and maths as well. Yeah, so it's tough. Yeah, but
at the same time, Tom, you have to remember that you doing different things that are exercising your left side of the brain, you're right. You have a better way and a more holistic way of actually looking at a problem. Sometimes compared to somebody who can just be sort of, I'm just mathematics or I'm just physics. Like you quite you can think of analogies to kind of, okay, where else do I see this and in what context? What else
it's good, well-rounded sort of.
Exactly. Super stuff. I'll send you the video then for today.
Thank you.
I'll send you the board work, and what I will try and do, because I know that you've still got some of those questions on those papers, I will collect some past OCR questions on this kind of stuff, and I'm going to email them to you. Now, those are on my Google Drive. I'm going to have to do a bit of digging, but I see that you might benefit you. I'm going to have to do a bit of digging. So if you don't get them today, Conrad, you definitely
no worries.
Yeah.
I just got a text. I'm free any day. So if you choose which day you're most happy with.
Okay, I would rather prefer if we so today's Friday. Why don't we meet up? Why don't we have a lesson on Monday, Conrad? Because in that way, it's out of the week, it's out of the way, and you've got the week to practice what we've learned, as opposed to keep.
That sounds really, really good.
Do you know what I mean? And then if you get,
that sounds good.
Be like, okay, I got stuck on this and this and this, and then you have time to sort it out.
Brilliant.
Super.
That works.
Shall I say Monday and
same time?
Monday. Yeah. I know teenage years. Most of the teenagers don't know what 7 or 8 o'clock is, so I'll work with. I'll work with. Do you want to say 6 p.m.?
Yeah, sounds good.
Cool, nice. And Conrad, I hope you found that useful. And
I really did.
Awesome. I look forward to
Thank
seeing
you very
you
much.
on Monday. Enjoy your rest of the weekend.
I'll see you on Monday.
See ya. Cheers again for Eddie as well, yeah?
Yeah.
Appreciate it. Cheerio. Ta-da. Cool. All right.